My dear students, in today's video, I will start the mathematical modeling of DC motor by field control method. Already I have discussed the mathematical modeling of DC motor by armature control method. So let us start today the video lecture on field control method of DC motor. So let us start. Mathematical sorry of DC motor field control method. Field control method. So already I have discussed about the DC motor. Here the DC motor used as DC servometer, therefore it uses the linear magnetization characteristics, therefore the flux phi is directly proportional to um, the field current. So already I have discussed this in the armature control method, that is we are using the DC motor here as DC servo motor. Then I will design another control system. So how to control the speed of the DC servo motor by field control method? If we'll consider the field control method, then we have to make the constant of the armature current, whereas field current will be varies. So let us first draw the circuit diagram for field control method. Let us assume that this is the field resistance and this is the self inductance of the field coil, and this is the applied voltage to field, that is called control voltage or excitation voltage. And let us assume that the field current here is IF. So this is the motor, this is armature current IM, armature current IA, and this is the shaft of the shaft. So let us assume that this is connected to a load. So the torque developed by the motor is Tm and the moment of inertia is J, and the angular displacement theta, and let us assume that the viscous friction coefficient is B. So this is your LF. So this is the circuit diagram. So already I have explained in the armature control method. Here there is no note to explain again. Therefore, let us directly write the torque equation. So here let Rf is equal to resistance of field winding, Lf equal to self inductance of field coil, If equal to field current, and Ef control voltage or excitation voltage. Then J is equal to moment of inertia. Then B is equal to coefficient of viscous friction, and Tm is equal to torque developed in motor. So then theta is equal to angular displacement So already I told you the here the DC motor used as DC servo motor, therefore it uses the linear characteristics of the magnetization curve. So the flux, that is phi, is proportional to field current IF, or phi is equal to KF into IF. So torque Tm is proportional to IF and Ia, or Tm is proportional to, putting the value of phi here, here phi into Ia. So Tm is equal to Kf into If into IA or Tm is equal to K1 Kf If Ia. Here these three K1 Kf and Ia, this is a constant, because here we have considered the field control method, therefore armature current will be constant. So torque Tm is equal to Kt dash into If. In case of armature control method, we have taken the motor constant as Kt, therefore here in field control method I have taken this as Kt dash. So this is the torque equation, that is Tm is equal to Kt dash into If. If we will take the Laplace transform for this equation, therefore Tms is equal to Kt dash If of S. So let us assume that this is equation number 1. So now applying KVL, Kirchhoff's voltage law, to field circuit. So this is the field circuit. This is If, this is Lf, this is Rf, and this is Ef. So we can find out the field equation, that is Ef is equal to If into Rf plus Lf into dIf by dt, or now we can take the Laplace transform of this equation, that is Ef of S is equal to If of S into Rf plus L F of S into If of S. Here I have taken the zero initial condition, so therefore the Laplace transform of Lf dIf by dt is equal to Lfs and If of S by taking the zero initial condition, that is If of 0 is equal to 0. So let us assume that this is, or we can simplify this equation again, or Ef of S is equal to, we can take common here, If of S, that is Rf plus Lf into S. So let us assume that this is equation number 2. So we can find out two equation here. This is the equation number 1 and this is the equation number 2. That is Tm of S is equal to Kt dash If of S. This is equation number 1, and this is equation number 2. Is equal to If of S into Rf plus of S. So now we can find out the motor equation from motor equation again we can find out, that is Tm is equal to J d square theta by dt square plus b d theta by dt. So if we will take the Laplace transform of this, so Tm of S is equal to J square theta of S. Here also I have taken the initial condition 0, so Bs theta of S. So this is equal to, we can put here, that is Kt dash If of S. So If of S is equal to, you can take common here, that is S theta of S, that is Js plus B divided by Kt dash. So let us assume that this is equation number 3. This is equation number 3. If we will put this equation number 3 in this equation number 2 by putting this, the value of Ifs here, then we can find out the transfer function of this equation. So Ef of S is equal to, that is S theta of S Js plus B into Rf plus Lfs divided by Kt dash. So we can find out the transfer function of this system, that is field control method. So transfer function is equal to output is the displacement, that is angular displacement, that is theta of S. Input is the control voltage or excitation voltage E of S, which is equal to Kt dash divided by S into Js plus B into Rf plus Lfs. So this is the transfer function of the field control method. So now we can write the block diagram representation of this system. So block diagram is like this, that is that is 1 by LFS plus RF. IF of S KT dash KT S plus JS plus B. This is the theta of S. So this forms a open loop control system. So thank you very much.